Okay, so now let us look at an example. You remember I talked about the example of an SRAM cell where we wanted to improve the write operation without degrading the writability of the cell.
Yes, sir.
Hmm? So
Yes.
I know some of us are circuit designers over here, so it may sound to be very easy and intuitive to you, but I have tried to contextualize the problem and make it simple enough for everyone. So those who are not circuit designers, don't feel disheartened and don't think कि आपको समझ में नहीं आएगा. I've tried to make it simple enough so that everyone can understand. Anyways, finally, when we come to see the Triz, that is the beauty of Triz. Triz may start from a specific problem, but will take you to an abstraction where everyone can participate. So just to understand the problem, it may appear a little difficult to you, but once we arrive at the function model, you will see that you can equally well participate. So all of you just pay a little bit of an attention. Even if you do not know circuits and you do not know the SRAM cell well, we will just go through it and we will handle it. So the context of the situation is that low power consumption is a very key, MPV for portable devices. You want your cell phone to consume less power. You want your laptop to consume less power. Any portable device, even the earphone that I'm putting in my ear, I want it to consume less power so that the overall lifetime without charge increases, without recharge increases. And for ICs that we use in all these electronics devices, power is very strongly dependent on voltage of operation. So in one of your basic electronics courses that I believe every one of you have done, you might remember that the formula for power consumption is CV square F. That is the capacitance that you are toggling, the voltage square into frequency at which the toggle happens. This is basic circuits, which you may have done. Even in school, you may have done these basic circuits. So because power consumption is dependent on square of voltage, if you can reduce voltage of operation, you can reduce power very significantly. Now, to reduce voltage of operation of ICs, typically functionality of regular digital circuits that you have studied is not impacted. However, some circuits like SRAMs get impacted. SRAMs are special circuits which are like SRAMs are memories which are very dense, where even non-CMOS components are used so that you can have higher density. And due to this non-CMOS circuit operation or non-symmetrical circuit there are some reasons for which circuit can fail at low voltage. We'll just look at what those reasons could be. So both read and write operations on the memory degrade at low voltages, and we need to improve them. So if you want to really save power, we need to go to low voltages. If you want to go low voltages, then memory read and write operation has to be improved. And this can be managed by increasing the area. But just like power is a very important MPV, main parameter of value for portable devices, area is also a very important MPV, because if the area degrades, then the cost of the system degrades. One of the main reasons why the cost of electronics is reducing over the past so many years is that we are able to shrink area of devices. And as we shrink area of devices, we are able to fabricate more devices in the same time. And therefore, the machine depreciation cost and all those costs reduce. And we are able to reduce the cost of electronics. So you cannot really increase area also. So the obvious solution, which was there, that increase the area to improve read and write, that doesn't work. So now we need to analyze the problem. So we go into, but before we go to analyze the problem, let us look at what a 60 cell or a 6 transistor cell look like. So 6 transistor cell is, so this is called a 6 transistor SRAM cell because there are 6 transistors in it. That's pretty layman. And just to refresh, a transistor is like a switch. which could be open or it could be closed, partially closed or fully closed, based on what is the value at its gate. There are two types of transistors, PMOSs and NMOSs. PMOSs, we are calling them pull-ups in a SRAM cell, and PMOSs are open. That is, they do not pass any current when the gate is at 1. And they are closed when the gate is at 0. On the other hand, NMOSs are open when gate is at 0 and they are closed when gate is at 1. So they pass current when gate is at 1. SRAM is a type of memory. You also have DRAMs, you also have flash memories. SRAM is a type of memory which is typically used for caches in your system. When I use the word cell now, I would actually be meaning a storage element. That this is a storage element. And content of the storage element is a 0 or 1. That is what you can store in any digital electronic circuits. You know, it is about 0 or 1. So the content of a cell could be either 0, you stored a 0 in a memory cell, or you stored a 1 in a memory cell. Read operation is, I want to know what is stored inside the memory cell. Write operation is, I want to store a new content in the memory cell. So this is the 60 memory cell, 60 SRAM cell. And let me explain the write operation to you. So there are these two. So this is a latch. This is one inverter. This is another inverter. So this, in those terms, is a latch. Are you able to see this? Especially CS and non-EC folks. I'm taking you back to digital electronics and basic digital circuits and basic electronics.
Yes, sir.
Clear? So you're talking about a latch, and there are two access transistors, pass gates. We call them pass gates. And the two nodes of the latch are named as int node T and int node F. Int internal, node true, internal node false. When I say internal node true is 0, I'm saying that the content of the memory is 0. That I have stored 0. When int node T is 1, I say I have stored 1. Now in this circuit, I want to write. So it already stored a 0. If I want to change the contents, it means I now want to write a 1. How do I write a 1? To be able to write a 1, what is actually done is this node, BLB node, that is taken to 0, while BL node is maintained at 1. And then this signal, which is called as word line, I've acronymed it as WL over here, goes high. So can you remind me? This is a NMOS. What happens when the gate goes to 1? Does it start to conduct or does it become open? Is the switch open or closed now when WL went to 1?
Sorry, it's closed.
It's closed. So it will now, the current can flow through it. So what are we looking at now? We are seeing that there is this node which is at supply level. Let us say VDD supply level. And there is this another bit line which you have taken to 0 level. And in there you had stored a 1. And in here it had stored a 0. So what will happen? Because the switches are closed now, current will start to flow from here. And the current will start to flow from here also. Are you able to see this? Once the word line is selected, current starts to flow. Int node F starts to discharge through this particular pass gate. And int node T starts to charge up because the current is flowing there also. Now, one thing is that this bit line is a very big capacitor. These bit lines are very big capacitors. The internal nodes are small ones. So these capacitors have a very strong role to play. Over here, since the big capacitor is at 0, this NMOS has to transfer 0 to the internal node. Over here, since the big capacitor is at VDD or 1, this NMOS is expected to transfer a 1 to the internal node. Now the challenge is that NMOSs do not transfer 1 very well. So the current that is flowing over here is lesser than the current that can flow out of here. Okay. So what happens? We see that because this node, this current is lesser, the current on this side is lesser, we actually need current from the PMOS also to come into picture to charge this side up. So this can discharge to 0 easily, but to charge this side up, you need this PMOS to come into picture, the pull-up to come into picture. Okay. Now the challenge is that this entire thing, because the current over here is also less, the current over here is also less, the overall charging time or overall performance of the system degrades. Now, one simple solution would be somehow make this strong. But if you make this strong, then this also becomes strong and this starts to conduct current. Okay, so that is a harmful function. This should not conduct any current. This PMOS should not conduct any current. If I make it strong, it will start to conduct current. So that solution may be tricky to handle. We cannot really go that way. So then what we did was you know, as I was mentioning, you want to discharge this and you can make this one stronger, but you know, this is not really a desired solution. So pull-up is this PMOS is designed to be weak. And since this is designed to be weak, the overall performance degrades. The write is slow and you want to increase the slow. So we made the function model. We listed down all the components over here. We filled the interaction matrix. Those of you who use a tech optimizer, you are very well versed with this kind of a image, huh? You've already seen this. So we filled the interaction matrix, we made the function model, and we also identified, you know, harmful functions wherever there were. And then we made the model. You notice that we have these super system components, word line, supply, ground node, bit lines, bit line bar, and so on. And there are two targets, int node T and int node F. Int node T needs to charge up and int node F needs to discharge. And what are the insufficient functions? We know that the pass gate T charges it very slowly and the pull-up T also charges it very slowly. The harmful functions are that we wanted this pull-up to be off. We wanted this pull-up, so यहाँ पे गलत लिखा हुआ है. This is F. Okay. We wanted this pull-up to be off, but this pull-up is not really off. It starts to charge int node F. As it is discharged, as this pass gate starts to discharge it, this pull-up starts to charge it. So this is a harmful function. And then we also want to see if this discharge can somehow be enhanced. If this discharge is fast, then this pull-up can turn on fast and we could again recover some speed. Any questions till now? So now we are out of this transistor and you know, signal business. We're now talking about a function model where there are some harmful functions and there are some insufficiently performed functions. This language you should be able to understand. That is where I'm asking any questions.
So here the dotted lines are representing the functions that are not performed like to the level. Yeah,
yes.
Sufficiently.
Insufficiently
insufficient.
Excessive or insufficient.
I'm sorry?
The dotted lines are excessive or insufficient functions.
No, excessive would be dark line. Dotted lines are insufficient functions. So that is the tech optimizer tool. It automatically does it like that. I did not do anything separately. Tech Optimizer did it. I just told it is insufficiently performed and it made a dashed line there.
Sure. Yeah.
Any questions? Any more questions? Is this function model clear now?
Yes, sir.
Okay. So now using this function model, we then said, okay, there are these problems there which we want to solve. We then went to CECA, cause effect chain analysis. What is the symptom? Write operation is not efficient when VDD is slow. When we are operating at low voltage of operation, then write operation is not efficient. Why? Two reasons. 0 is not written well and 1 is not written fast enough. So 0 is not written well means internal node is not discharged. Why is it not discharged? The answer is either the pull-up device is very strong or the pass gate device is very weak. Why is the pull-up device very strong? We say, okay, pull-up device is strong because the control VGS is very high or the size of the pull-up is large. And the pass gate is weak because pass gate control signal VGS is low or the pass gate size is small. So this way we go and we identify what is the what could be the reason. So we stopped where when we reached at say something like VDD is high, VDD is low and all that. Why did we stop there? Because we said that this is the specification. Now I can't change it. VDD is low because that is what the customer wants. If VDD is low, then I can't, this is the specification. So I have to solve one of the previous problems over here. Is that okay?
Yes, sir.
So now we went into using ARIZ. We said now that we've kind of made the function model, done the CECA, let us define the problem. What is the engineering system problem? The engineering system problem is that if pull-up is weak, then it does not charge int node F. But because it is weak, it charges int node T very slowly. So this slowly is the thing. So it does not charge is the right thing, but it charges it very slowly. I could reverse this contradiction. I could say if pull-up is strong. So मैंने पहले कहा कि if I make pull-up weak, and then I say if I make the pull-up strong, then what happens? It charges this node rapidly. The speed wala problem tha, that gets solved, but it also charges int node F. So a harmful function has started to appear. So now we formulate a statement, a mini problem, which is that it is necessary that pull-up allows discharge of int node F and speedily charges up int node T with minimal changes to the system. So this minimal changes to the system is a very important phrase that we have to use. Okay. So what are we saying? What are the best of those two? We said we do not want to, we want to discharge int node F. Does not charge, or we want to discharge int node F, allows discharge of int node F. That is the benefit of the first engineering contradiction. And the benefit of the second engineering contradiction is it charges rapidly the int node T. So it charges speedily the int node T. So आपने दो engineering contradictions लिखी and उन दोनों को mix करके you formulate what is called as the mini problem. This is the first step of ARIZ. Is this clear?
Yes, sir.
So now we go back to the function model and we say, let us identify the products. So what were the products that we said? There are two nodes, int node T and int node F. Both need to be acted upon. Both are products. Then in the terminology of ARIZ, there is a definition of what is called as a tool. So what is the tool? Tool is that component which is acting directly on the product. What is that component? जिसके लिए हमने engineering contradiction लिखी, that was the pull-up. So for us, the tool is the pull-up. And then we write down two states in which the pull-up could be. state one is it could be weak and it could be strong, or let us say not weak. So are you getting the sense that I'm already now tending towards a physical contradiction, because there is this one variable, strength or weakness, for which I have defined two logical and very valid requirements. It has to be weak and it has to be strong. They are opposing requirements on a particular variable. So I am automatically now formulating a physical contradiction in a way. So I now graphically put the system, put this thing. The engineering contradiction one said the pull-up is weak. If the pull-up is weak, it does not charge int node f, so that is a regular function, but it charges slowly int node t. So you see, this is a dashed line. However, if the pull-up is strong, there is a harmful function over here. It charges int node f, but it charges rapidly int node t. So now you have two substance field models of a possible solution. Out of these two, which one would you use to take forward? Which one would you take forward according, like, आपकी common sense क्या कहती है? I know आपका answer मैंने नहीं बताया अभी तक. What do you think should be taken forward? Which one should be taken forward, EC1 or EC2?
EC1.
Why?
So because the node T is charging slowly in EC1, but if we see EC2, then we see node F is also charged, which is harmful function.
Any other ideas? Anyone?
Sir, I think based on what type of solution we would try to approach, if we go with EC2 as well, then we can perform trimming to, let's say, eliminate that harmful function.
So what would you trim? Yeah, so int node f is a target and pull up is the tool.
Yes, sir. I understand.
You can't trim product and tool, both of them you can't trim.
Yes, sir. I think that's why the reason
EC1.
is we should go with EC1, because we cannot trim the very component that on which the function, like we are performing a function.
This is the main function of the system. No?
Yes, sir. Main function.
This is the main function of the system. You cannot trim that target there. So EC1 is chosen because there is no harmful function there. EC2 has a harmful function. So whichever of these two contradictions is better. Now it may happen that in another example that you pick up, there is no harmful function in either, but there is some excessive function somewhere, and there could be a preference in terms of specification that, okay, I want the area to be less. So if they want the area to be less, then you would choose the weak one, because to make a strong one, you will have to make the device bigger. So there could be other such constraints which could help you choose the engineering contradiction to be taken forward. But over here in this particular example, it is very simple. Because there is a harmful function in the second engineering contradiction, we don't even consider it. We simply pick up the first one. Is that okay?
Yes, sir.
Hmm?
Yes, sir.
So we picked up that engineering contradiction and we say, we rephrase it. We say, okay, if pull-up is weak, pull-up does not charge int node f, and it charges slowly int node t. Now we exaggerate. That is ARIZ step 1.5 and 1.6. We exaggerate the contradiction. We say pull-up does not charge int node f, but it charges very, very slowly int node t. And then we bring in this X factor. This X factor is something which we do not know. What we'll do, we do not know the answer yet, but we say it is necessary to introduce an X factor that enables pull-up to not charge int node f and charge rapidly int node t without any harmful consequences. Now, this without any harmful consequences is also a very important phase. Because, see, we had chosen EC1 simply because it had no harmful functions in it. So we do not want to do something, introduce something else which introduces harmful functions. So this is also a very key requirement that we have to put on the X factor that we are talking about. What is this X factor? We do not know yet. As we move through the flowchart, as we move through the algorithm, we may find out, and that could be the solution. So the mini problem or the problem model has no substance field diagram per se, because there are no fields, there are these components only. So we simply say that, okay, we want to introduce an X factor which charges rapidly and does not charge int node f at all. Then we go to part 2, where we analyze the problem model now. We look at if the operating zone and space is different. Yes, they are different. Int node T, for int node T, the requirement is that the pull-up should be strong. For int node F, the requirement is pull-up should be weak. Huh? What about time? Oh, the time is the write duration when we are trying to write into the memory cell. Now that is the same for both int node T and int node F. I want to start to write on int node T and int node F simultaneously. So there is an overlap. Since there is an overlap, I realize that separation in time may not be a solution to this problem. So separation in space, there could be a solution. Separation in time, there may not be any solution. And then I start to write down substance field resources at various levels. What are the system components? I write down all the system components and their parameters. So size of pull-up is one variable, conductivity of pull-up is another variable, capacitance of int node is one variable, size of pass gate is, so all these are resources. I could play with all these resources to solve my problem. So I am trying to write down all the system resources and making a table out of them. And I write down the environment resources also. Supply levels, word lines, bit lines, everything I try to write down. And I also write down inexpensive resources. Could the adjacent cells, there's a cell right next to it, can I use it? These are inexpensive resources, which may not be, which you may not have put in the engineering system initially. But you just then see, can the adjacent cell also be used somehow? Then you go to defining the ideal final result and the physical contradiction. So X factor, so now we come back to the X factor there, and we say X factor itself charges int node T rapidly and preserves the ability of the pull-up to not charge int node F without changing the system much and without any harmful consequences. Now we see if there is some X factor amongst the resources that we had identified here. So we go resource by resource. Size of pull-up itself charges int node T rapidly and preserves the ability of pull-up F to not charge int node F. So I write down bilkul mechanically. I just write down X factor ki jagah. I write down all these resources one by one. So I create a long list. You will see I have created a long list of 12 such things. VDD itself charges int node T rapidly and preserves the ability of pull-up F to not charge. Same language, but I've just changed the resource. Ground itself does that. Word line itself does that. Exactly the same thing. And I mechanically write it down. That is steps 1 and 3.1 and 3.2. And then I go to the next step. I say, let me put in the values now. The size, the X factor was that size of pull-up should charge this and not charge that. So now I want to say, how should the size of pull-up be to be able to charge this? And how should it be to not to charge this? And you will notice that I have automatically created engineering contradiction. And I have created so many engineering contradictions all at once. See, when a technical contradiction is available or when an engineering contradiction is available, it is not easy to transition from engineering contradiction, which is at the symptomatic level, to a physical contradiction. And by using this language of X factor and listing down all the system resources, I have arrived at so many physical contradictions all in one go. Are you able to see this? Any questions till now? Is this clear till now?
Yes, sir.
Viman, Om, Sanskar. Now we're not talking
Yes,
about a
sir.
circuit at all. Now we are just talking about this model that we had created. Om, Sanskar, Soumyadeep.
Yes.
Okay. So now we look at these engineering contradictions. So there are some engineering contradictions already there. And at some places, you see there is no contradiction. It says size of pass gate should be large to charge int node T rapidly and also discharge. So there is no contradiction. I know there is a possible, so this could be a possible solution there. Conductivity of pass gate should be high to charge and also discharge. So where there are no contradictions, there clearly could be very easy solutions. Now, if you think that that is a solution, what would happen? You say, okay, I will increase the size of this. If you increase the size of the pass gate, the area would increase. So when you will go to step 7, you say this is the solution, you will directly jump to step 7 from here. And step 7 would have said, oh, this solution increases area. Area is also an MPV, so this solution doesn't work. So you may come back to either step 3.3 or then you go back to step 1. We do not know. But it does point you to some solutions right away. अभी आपने physical contradiction को resolve करने की भी बात नहीं करी, and there are some solutions which start to appear out of this analysis. Are you able to appreciate this?
Yes.
Yes, sir.
So जब आपने वो flow chart देखा था, this one, तब आपको शायद समझ में नहीं आया होगा कि ये कहा क्या जा रहा है, सॉरी, या कि अभी आप थर्ड पॉइंट पे ही हो, फिजिकल कॉन्ट्रडिक्शन बस अभी डिफाइन करिए और आप कह रहे हो सॉल्यूशन भी आ गया क्या, है ना? तब आपको ये वाला पॉइंट इतना समझ में नहीं आया होगा. बट नाउ यू आर एबल टू सी दैट द सॉल्यूशन इज राइट देयर. There are, when we go through the process itself, when you are talking about resources of the system, super system, subsystem, when you've done just this much only, some solution may emerge automatically, and that could solve the problem. You directly go from point 3 to point 7. You don't even need to go to this part. So are you able to see this? Why the flowchart had a solution in right there even before resolving physical contradictions? Because that is what this tool does to us. So we say there is no contradiction here, no contradiction here. And for each of those 12 X factors, I try to find it out. Now for the 12th X factor, I can't do anything. What was the 12th X factor? Adjacent cell itself charges int node T rapidly and preserves the ability of pull up F to not to charge. So now adjacent cell I had put in as an inexpensive resource there. But what happened? Adjacent cell was not even interacting with my int node T or int node F and anything. So there is nothing that I could do to it. So if there was some extra resource that you have put, you will automatically remove it from the system now. And there are some contradictions. There were some no contradiction things. Now you start to refine it. So now you're talking of using what is called as some magical component. Magical component, particles which are available in pull-up to improve its conductivity to charge int node T rapidly, but not available in the other pull-up so as not to charge int node F. Wherever there are contradictions, you try to see if there could be, you could talk about some magical particles there. Magical particles. So particles are not available in pull down 1 to have low conductivity to charge int node S, but they are available in pull down, the other pull down, to have high conductivity and not to charge the other int node. So you talk of it in terms of particles. Basically, you are kind of expanding your resources. Can there be something else? Can there be some particle, some way to get that? And you then also talk about in the region of the int node F, because you knew that the operating zone can be different. You could separate by the space. So you now talk of it in terms of space. In the space of int node F, the node that needs to be charged up, conductivity of devices changes automatically in such a manner that it charges rapidly. You see, we are using some terms automatically. It automatically does it. It happens. We already used the term region, so that I can already start to think of separation in space. So we formulate the problem in a particular manner. And we now start to resolve the physical contradictions. For example, size of pull-up S should be large to conduct, but small. So for symmetry requirements, pull-ups have to be physically equal. But I could possibly use the principle of segmentation because I know that I could separate in space. If I can separate in space, then the principles, inventive principles I could use there were segmentation. If I could segment and evolve an independent control for pull-up T and pull-up F, then I could have an answer. So there's a possible solution over here. Then it says conductivity of this should be high in this region and low in that region. So due to symmetry requirements, conductivity is designed to be equal. But can I achieve IFR2 by using other resources in the system? We do not know. Then 3 and 4, we said there was no contradiction, so there are clearly solutions that are possible there. 5, again, there's a solution that is possible there. 6, size of pull down T should be small to charge int node F, should be large to charge int node T. So again, there is a possibility due to symmetry reasons that we cannot do it, but can I use segmentation again? So again, because they are in different operating zones. So again, there is a possible solution over here. So just going through this flowchart has highlighted some possible solutions to me. There is a possible solution with 8th resource also, 9th resource also, 10th and 11th also. So there are so many possible solutions. Now, for each of these solutions, directly from step 3.6, I can actually go to step 7. And you will see that we were able to, for example, separate VDD. So this solution I had shared with you even in the introductory lecture. You remember? We had shared the solution where we said that we would split the supply voltages for the int node F and int node T so that it could charge the int node F fast, but not discharge the int node T. You remember this solution? We had talked about it. Us samay reflect nahi kara hoga, but that is a patent that we had filed. I will just show that slide to you again. Just give me a second. Let me just show you that slide. And this was so long back that I'm almost sure you might have forgotten about it. So let me just come to it. Are you able to see this?
So,
Where
yes.
we said that where we have actually split the we've actually split the supply voltage, segmented the supply voltage, given different body bias voltages also, and we could say that the solution Not only improved writability, it also improved speed. And this was at almost zero cost, because splitting this, we had area there. We did not have to put in any additional area. We just had to put an additional wire there. So you see, यहाँ पे भी हमने वही contradiction लिखा है. PMOS should be weak to improve writability. PMOS should be strong to improve write speed. So what we discussed just now, I had already hinted that to you long back. Any questions? We are separating VDD. We could separate G and D. We could do all that. And that solution finally worked for us.
Yes, sir. So like in this question, like maybe we can apply all the possible solution and then compare the results and then find out which one works the best.
Yes, we did that. जैसा मैंने आपको कहा, I'm not giving all the details to you, but for example, I said this size of pass gate. It says it should be large. It's such a simple solution. There's no contradiction. When we went to step 7, we saw, oh, area is increasing. So we rejected this solution. Capacitance of end node T and F should be small. I want to keep it small. This is a possible solution, but how do I keep it small? This is a parasitic capacitance only. There is nothing that I could do. This was not really a solution. So there was no contradiction here. This appeared to be a solution, but this was not really a solution. So many could be fake, but finally, because there are so many of the possible solutions there, you could arrive at something really meaningful and interesting, finally.
Yes, sir.